Equilibrium.
Gibbs free energy was the last part in thermodynamics.
Yes. With
Yeah.
that thermodynamics in it, yeah. So equilibrium is basically, just think of Thanos. So if something is in equilibrium, it means that it's in balance. Like if it's a process, whatever forward moving process is equal to backward moving process. So everything in balance, as Thanos wanted it to be. Okay, so that's what we'll deal with in this whole chapter. Three main parts to this chapter. So the first bit of it deals with physical and chemical equilibrium. This is basically like an intro where you can find equilibrium and what it looks like. Like if it's a physical equilibrium in solutions, in vaporization, in crystallization, whatever it may be, and general factors. Why do we study about equilibrium? Like what kind of information do we get out of it? And what is it affected by? Temperature, pressure, catalyst, reactants, products, all of that. So general intro to equilibrium in physical and chemical processes.
How
Then
many classes will this chapter take?
I'll come to that. Then you have ionic equilibria. So ionic equilibrium in three cases. Actually two cases in ionic equilibrium. So in the case of acids, and you have bases. So we look at basic, what sort of equilibrium is set up when you dissolve acids and bases in water, and some special additional stuff comes up if it's a weak acid and a weak base in for with respect to your calculations and all that. And then the third part of it, all related to equilibria related to salts. So hydrolysis of salts and what sort of equilibrium is set up in that case. And because of that equilibrium, you start getting acidic salts, basic salts, and all of that. So salts, buffer solutions, all of that. Okay, so three main parts to this chapter. I was hoping that we usually takes about 3 classes. So this we can do in one class, this we can do in one class, this we can do in one class. Depending on questions and other factors, we may require plus one more class, but we'll see how it goes. So that's what I was hoping to do. Like I was hoping to finish off physical and chemical equilibrium in this class up to like Le Chatelier's principle. Yeah. So I think I've asked you guys this before also, but now that you have completed the chapter, you've been having your revision classes at schools also. How do you feel about this whole chapter? It's a huge chapter. Like there are 3 major sections to it and everything. So how do you feel about it? Which part seems easy? Which part seems difficult? So based on that, I'll modify how much
It's very content heavy. Like it might not be very difficult, but it's very content, like knowledge inclusive.
It's all new stuff. So nothing to memorize.
Organic. In organic way, just theory, right? Back we've learned that before. It's just like they just segregated it. Nah? Here it's like you have so much content, you actually have to like understand it and also.
Correct.
And like, I can't recall the math part right now, like how we use logs and all. So I'm actually a bit concerned about this chapter. So
that you will come across in Ionic Equilibrium. This part is math heavy. So this is majorly like theory, understanding what it is, examples and all that. This part is math heavy. This part also has math, but much easier compared to equilibrium. Yeah. Comfortable only with ionic equilibrium. Okay. Okay.
I think, as you said, right, about in the start, about that the as it goes forward and reverse, I'm like, like, okay with that concept, but not very much sure. Other than that, even the maths concepts and all, those are like okay. I know the formulas and all, but yeah, needs more practice.
Yeah. So the more this is like approach this chapter the way you would approach physics, in the sense that how long it took for you guys to get comfortable with physics and being able to solve the problems and all, this chapter is going to be like that. The more time you spend with it, the better you'll get at it. And as Adat says, it is content heavy, but it's different from inorganic chemistry, that inorganic may it's like reading a story. You're like, oh, phosphorus does this, phosphorus does that, nitrogen does this. Here it's like you need to, it's completely new concepts that you need to understand more than memorize. So that's where the major difference is. We won't get any theory based questions, but it's more of understanding and application where it's going to be new. Sanat, why do you say you're not good with this chapter, like so far, or is it just intimidating?
I do not like it.
No, this is actually, it's going to be fun. It's just a little daunting because it's completely new for you guys. And this is not to scare you, it's just to keep you mentally prepared so that, when we're in the thick of it, it shouldn't come up as, oh, it's still going on, what's going on. Just be a little prepared. But otherwise, it's very.
Like in school, when we did the processes wala part, like backward movement, forward movement, I got a bit of it, but I'm still blank.
Oh, okay. Anyway, we'll start right from the beginning, so don't worry about it. Okay.
Also, we got marks distribution of all the chapters. So I just sent you that, okay?
Okay, thanks, Vishal. All right. So we'll look at physical equilibrium first. Just like the difference between physical properties, chemical properties, exact same thing, physical equilibrium versus chemical equilibrium. Okay. So whenever you have equilibrium set up in a physical process, in a physical change like evaporation, condensation, that sort of a thing. So that sort of a thing is called physical equilibrium. Okay. So I'll quickly go over the characteristics and then we'll look at specific examples of processes. First is all measurable properties are constant. So whenever there's something in physical equilibrium, actually I'll take an example so it's easy to visualize. Okay. Let's say you took a saucer, put some water on it and left it out, like just left it out. Or instead of in a saucer, let's say, yeah, I think we'll do this solution. Let's say you took a glass of water. Okay, a little bit, 3/4 filled up, and add some sugar in it. Sugar or salt, whatever. If I add 1 spoon of sugar in it, what will you observe? Like added 1 spoon of sugar, dissolve it, then what happens?
It gets dissolved.
Correct. Then I add 1 more spoon of sugar and mix it. Then what happens?
You mix it down.
It gets dissolved until it gets saturated.
Until it gets saturated, right? So let's say I add like 5 whole spoons of sugar after that. Then what do you observe?
Sugar
After the
water.
point, it will stop getting dissolved.
So to a saturated solution, if I add more sugar, it will stop getting dissolved. So you can see that sugar is still there at the bottom, right? It's not getting mixed up in water. It's still there over here, right? That's what you see. So that brings us to the first characteristic of a physical equilibrium, that all the measurable properties are constant. Okay. So what is happening in reality is that if I just zoom into this, what is happening is that, so there are sugar particles and there is water all around them, because you literally put the sugar in water, and there are sugar particles in water that have dissolved. So this is not like even though it is saturated and this is like extra sugar, even though it looks like nothing is happening to the naked eye, at the molecular level, this sugar is still dissolving. But because it has reached the saturated point, like there is no more space between the water molecules for more sugar to occupy it. So if one particle of sugar goes in the solution, if this is trying to get dissolved, it is going to push an already dissolved particle of sugar to crystallize out. Okay, so this motion is constantly there, but you can't see any change happening here because the rate of the forward process, like the rate with which sugar is being dissolved, is cancelled out by the rate with which the sugar is coming out of the solution. So because they both are perfectly in balance with each other, at any given point, if you measure the concentration of this solution, it's going to be constant. At any given point, if you measure how much mass of the sugar is, still undissolved, that's going to be constant. So all the measurable properties are constant. Doesn't mean that nothing is happening. The process is still taking place, just that whatever is the forward reaction, same is the backward. So the status quo doesn't change at all. Yeah, so that's like a classic, like this holds good for chemical equilibrium also, like properties.
Is
Like
this beyond saturation?
this is at the point of saturation.
I didn't get it. Like the cycle is what, all the blue and the black arrows are both sugar particles?
Yeah. So the black is the sugar getting dissolved from solid into aqueous, and the blue is the sugar that is already dissolved that's getting out, and like from solution it is turning into back to like a solid particle that is not dissolved.
If it had not reached the saturation point, then would this cycle still be there?
No. So the cycle will still be there, but the black part of the process dominates. So the rate of dissolution will be more. The other side, like the reverse, is going to be slower. So overall, because this part dominates, the overall effect that you see is that, oh, the sugar is, getting dissolved.
So the sugar which we see left out, like the sugar which we see after it dissolved, that is the sugar which was already dissolved.
If you
If we see,
sugar,
if
yeah.
we keep on mixing sugar, and when we start to see sugar just below the water, that sugar was already dissolved and now is back to the solid state. Is that what is happening?
Yeah. So it's the particles at a molecular level, they are constantly in motion. So it dissolves, something else comes out, then this goes in, then something else comes out, then this goes in, something else comes out. So that is the whole point about equilibrium. Like the process is continuously taking place, just that we don't see the net result because net result is zero. It's like balanced forces. Yeah, Sanat?
So like once it's past the point of saturation, the blue arrow would be like more dominant.
Correct. So that kicks into gear until both of these are in balance with each other. Yeah. Yeah, Adit?
So, ma'am, the example that you've given right now for solution, is it also similar to like a solution of Tang, like the drink how we use, like once it's saturated, like the sugar still stays below, and then
Any solution, yes.
Okay.
Yeah. So basically, I can write it as sugar solid. So because both the processes are taking place, it is denoted with this reversible arrow. Sugar aqueous. Yeah. So measurable properties, like in this particular case, we measured property matlab because there is dissolving involved. Concentration of this solution dekha humne. At any given point, like 10 minutes later, also if you see, it's going to be the same thing. That saturated point jo bhi hai. The temperature is going to be the same. Pressure to it won't be applicable here. the mass of undissolved sugar will be the same. Like whatever you measure, density, it's going to be constant when the equilibrium is established. Okay. Next, so equilibrium, like physical equilibrium, you will observe that it can be established only when it's a closed system. Closed system at any given temperature. Okay. Do you guys remember what is the difference between a closed system and an open system?
There's no exchange of mass in a closed system.
Correct. So if I end up adding more water, then there is more space, the equilibrium gets disturbed. Like more water, matlab more sugar can get dissolved. Then it's no longer at an equilibrium because again the black one will dominate. If I remove some water, then the blue process is going to dominate. So both the cases, the equilibrium will be disturbed. So if you want physical equilibrium to be there, it needs to be a closed system. You can't change the quantities of anything.
But we are changing the quantity, right? We are adding more sugar.
No. I have added like, I don't know, 7 spoons of sugar and I let it be.
Okay.
उसके बाद ही equilibrium establish हुआ. तब तक whatever was getting dissolved, it was getting dissolved. Yeah.
Do we note down the sugar example?
You can if you
Also-
want, it helps with your this thing. So we'll be doing like evaporation, condensation wale examples. Dissolution फिर से आएगा. Solid and liquid, gases and liquid bhi hai. All of that is going to come up later. For the properties, like if it makes sense to you guys, if it helps with your understanding, you can note it down. Ritu, you were saying something?
But I still didn't get how it's at the point of saturation. Like the amount of solute would have to exceed the amount of saturation, right?
Just beyond the point of saturation. Like think of it as saturate kar liya and added like an extra spoon after that.
Understood, ma'am.
Next, it is a dynamic process, like it's a dynamic system, yet it is stable. Okay, so dynamic in this case, like it is basically the opposite of static. Do you guys know what static means? Have you heard of this word? Have you come across, used this word before?
It means it's not
Static
interactive,
motion.
right?
One at a time. Rishit?
I have read it in physics, static motion, like solidness, like at rest or
At rest. So static motion does not make sense. But yeah. At
yeah,
rest.
I
Yeah.
think something like that. Yeah.
Kaveri, you were saying?
Yeah, I was saying the same thing. Physics.
Ritu?
I was thinking of something else. I'm sorry.
No,
I
no.
heard it from like the subject in 10th grade. I don't know why I remember it.
Yeah, same.
Yeah, like it's a lot of websites you were learning. I remember that's how I know. But I think dynamic over here means like the bodies are moving in like a constant motion.
Yes. Yeah, that's the sense that, and yeah, you need to take it in. So static matlab at rest, like nothing is going on, but dynamic in the sense, like it's the opposite of static. Like the processes are still going on forward, backward, like nothing has stopped. They are not, the particles are not at rest. Like sugar is still going into this thing, this is still coming outside. So it is a dynamic process, yet stable. So technically properties are constant, nothing is changing because it's an equilibrium. Okay, so that's what this point means. Unstable means like unsaturated solution may one process is dominating. So the mass of sugar like that is not dissolved is constantly decreasing because वो dissolve हो रहा है. But when the equilibrium is established, no, nothing is changing because whatever is going on, uska reverse is also taking place. So that way. dynamic yet stable. Next, fourth point, it is characterized. Okay, this is a good one. So it is characterized by
Ma'am,
yeah.
could you explain the sugar example with the dynamic distinguishing?
हाँ, dynamic means constantly moving. मतलब वो process हो रहा है. So in this example, the arrows, like the sugar is going into the solution, other sugar is coming outside the solution. That is constantly happening. As opposed to like बाहर कैसे दिख रहा है, we're just saying that, oh, that sugar is just sitting there, nothing is happening. But that's not true. Like whatever sugar you add, it is going into water. Just that something else is also coming out. इसलिए net change is zero. But that's the net change. The resultant is zero. But the process is still continuously happening.
By stable, do we mean because we're not adding any external energy or matter?
Stable, we mean that like there is no change essentially. Unstable means there is something changing, like concentration is changing, या फिर the mass is changing, or temperature is changing. But nothing of that sort happens. Like all the measurable properties are constant. So it is stable, like it's staying like that only. Like there is no change happening there. Next point, yeah, it is characterized by the constant value of one specific parameter. So this, we just gave a random word parameter because this one parameter, what it is, depends on what process it is. So if I'm looking at solution, constant parameter will be the concentration of the solution. So if I've dissolved, let's say there's 3 grams per liter of sugar, then it's always going to be 3 grams per liter of sugar, even though this whole process is taking place. Yeah. If evaporation condensation ke beech mein, if that is the equilibrium setup, then vapor pressure is going to be the constant value. If it's a physical process like boiling or melting or something, then the temperature is the constant value happening there. That way it differs from process to process, but depending on what process it is, one particular parameter ka constant value hoga. Thermal equilibrium, for example, usme temperature is always the same. Like even though the heat exchange is happening, because equal amount of heat is being exchanged, unka temperatures will remain the same. That way. Next.
Ma'am, could you go over the third point again about the dynamic one?
Like what part have you not understood, Rishabh?
How is it exactly dynamic?
Because particles to move ho rahe na. Like dissolving process has not stopped. Like the sugar is constantly dissolving. Just that uska opposite process bhi ho raha hai. So as long as the process is going on, we say it's dynamic. Static matlab there is no motion, there is no movement, everything is at rest, like there's no process going on at all. But wo nahi ho raha hai. So take for example, let's say you have 2 teams, like team A, team B. Har ek team mein, let's say there's supposed to be 5 people. To maintain 5 people in each team, either these 5 people can just stay on their own, in which case it is static, or like the first member from A can go to B, at the same time the 4th member can go back to A. Now because there is exchange happening, you're still maintaining 5-member teams only, but individual members are like constantly changing. There is like motion taking place. So that's dynamic. Static matlab jo hai A mein, there is no change at all. Whoever is in A is in A, whoever is in B is in B. So that's like static because there is no change, no one's running around. But in the case of dynamic, if one person is going there, at the same time the other person is coming here. So net result is that A, like team A may there's 5 people, team B may there's 5 people, but these individual people are not the same. Like they're constantly moving between teams. So that's dynamic. Think of it that way. Make sense?
Ma'am, can you explain the fourth one also again?
Yeah. Rishit, does that make sense? Got it?
Yeah, ma'am. So basically, it's like both of there is a exchange, but you cannot notice it because it's
Correct.
equal.
Yes, absolutely. That is what equilibrium is. Okay. Ritu, fourth point, it is characterized by the constant value of one parameter. So if I take the team wala example only, the parameter is the fact that each team should have 5 people. So that parameter is not changing, but the individual members are changing. There is like movement going on, the exchange is still taking place. So parameter can be something like pressure, it can be temperature, it can be concentration, it can be number of moles. It could be something, it depends, varies from process to process. But the thing is, yeah,
When you said like two teams, like what does that mean? Like between two reactants, between like the reactant and the product?
between what? Sorry, can you repeat that?
What does the two teams stand? Like what's the analogy for? Like is it like between the product and the reactant?
Oh, no. It's just to show you guys the difference between like just what is an equilibrium being established and what happens there. The two teams are basically two sides, like process ho raha hai na. So one team can be undissolved sugar, the other team can be dissolved sugar. One team can be liquid state, the other team can be gaseous state. So equilibrium, whenever we say equilibrium, uska matlab kuch process ho raha hai. Uska reverse process is also happening in the same, at the same rate. So A and B could be reactants and products. Like that's a before process and after process is what you can think of it as.
Understood, ma'am.
Yeah. Okay. Fifth. So the magnitude of this particular parameter we talked about. Magnitude of parameter shows how far the equilibrium has proceeded, how far the process has proceeded. Okay. So the one parameter that ends up being constant when the equilibrium is established, if you keep measuring it at constant time intervals, you can figure out, okay, process kitna dur gaya. So if I'm taking the dissolving wala example, I had mentioned that the parameter that's constant is the concentration. So if I start measuring the concentration of this water, like sugar water, right from initial, like pehle liya to it's purely water, concentration equal to 0. Then after dissolving some amount of sugar, it's going to increase it to 0.5 gram per liter. Then it will increase it, it'll be increased to 1.2 gram per liter. So that way this particular parameter will keep changing. And as it changes, I can figure out ki, okay, saturation पहुंचने के लिए, मतलब वो equilibrium पहुंचने के लिए, how far have I come? And the moment it hits 3 gram per liter and it does not change, that's when I can figure out that, oh, that parameter का constant value आ गया, मतलब equilibrium has been established. Make sense?
What is 0.5, 1.2? Like what is it?
Concentration of the sugar in this water. So in this particular case, I'm measuring the concentration. So the magnitude, so this particular number will tell me, okay, how far along have I come in this particular process of dissolving. Okay, and that particular parameter, it will keep changing. And then at one point, it's going to be constant. So when it is constant, I can say that, oh, it has hit equilibrium. Again, as I said, parameter can be either pressure or temperature or concentration or number of moles, or it can be vapor pressure. It depends on what process you're considering there. It can be mass, could be anything. Okay, so like these are just characteristics of physical equilibrium. Like this is how you will identify physical equilibrium, okay. This gives you an idea of, okay, how do I know if equilibrium is established and what is going on? Acha, if I say that there is equilibrium in this glass bottle, what does that mean? Kya ho raha hai isme? Okay, guys, make sense yahan tak?
So basically, it tells a number, like for example, heat. So it went from like 5 degrees to 10 degrees. Is that just that change you're talking about?
Yeah. So yeah, another example, like thermal equilibrium ke example lete hain. Suppose I have a block at say 50 degrees. And then I put another block on it, which is at 10 degrees. So this is cold, this is hot. So technically, like what physics tells us is heat is exchanged in both the parties. But because this is at 50 degrees, initially this is going to dominate the process. So in this situation, my parameter is temperature. So pehle, if I look at the temperature, upar, like cold substance ka, it was at 10 degrees, niche it was 50 degrees. Then this increases to 15, this decreases to say 47 degrees. This increases to, I don't know, 20 degrees. This decreases to 40 degrees. Like temperature will keep changing until they reach a point where both their temperatures are equal. So let's say that's like 30 degrees. So uske baad, whenever I measure, both of them are going to be at 30 degrees only. So my constant value parameter is temperature here, which got stuck at 30 degrees. And by measuring temperature, I can figure out ki, okay, how far has this heat exchange proceeded? Dynamic yet stable in this situation, heat is exchanged, but during all these times, 50 degrees was pushing more heat, 10 degrees was pushing less heat. इसलिए इसका temperature increase हो रहा था, इसका temperature decrease हो रहा था. But there came a point where the heat given out by this is equal to the heat taken in by this. And because there was equal heat exchange, they got stuck at 30 degrees. So यहाँ पे equilibrium established हो गया.
Ma'am, could you explain the concentration wala example?
Explain concentration, matlab what part were you not able to get, Kaveri?
This magnitude of parameter thing that you explained for 0.5, 1.2 gram per liter, I didn't get that.
So again, my parameter that I'm measuring to see whether equilibrium has set in or not is concentration. Again, imagine the process. A lot of imagination here, Kaveri. So initially, when there is no sugar, if I want to measure concentration of sugar, kitna value hoga?
0.
Then I added some amount of sugar. तो concentration का value क्या होगा?
0.5.
Yeah, like 0.5, these are random values that I took, but it's going to depend on how much sugar I put in, right? Then if I add some more, then what will this number become?
It'll increase.
It'll increase. So that's what, like it'll keep on increasing until I hit that point of saturation. So at which time it is going to be constant. So that's what like these two points are telling or explaining.
So I understood like characterized by the constant value of one parameter because that's when it reaches equilibrium. But when we say maximum parameter shows how far the process has proceeded using like the 30 degrees or the point of saturation, how do we show कि पहले क्या हुआ?
So that's what, like if I see concentration, say हमें पता चल रहा है because concentration is not changing, we figured out कि equilibrium has been met. But उसके पहले क्या हुआ? 0 से it has slowly started increasing, no? Depending on like with every spoon of sugar that I pour in, my value of concentration keeps increasing. So if suppose my equilibrium pe the value is 3 gram per liter, and if I see that its concentration abhi bhi 1.2 hai, then I know that okay, I need to pour in some more sugar. Like it shows me how much further I can go that way. Okay. All right. Next. So we'll get into some examples. Okay. So the first process, so H2O solid is in equilibrium with H2O liquid. So what is this process called? In case you know this process, see what is happening. What is this called?
Melting. Sorry, fusion.
Melting, fusion, yeah, absolutely. Now solid is in equilibrium with the liquid state. So we can also say this is solid liquid equilibrium. So this happens whenever there's melting or freezing taking place. So when the pressure is 1 atmosphere, our default we take is always like 1 atmosphere. Okay. At what temperature would you find this equilibrium being established?
At 0 degrees
273
Celsius.
Kelvin.
Yes, both of you are right. 273 Kelvin, which is 0 degrees Celsius. Okay. So as long as I maintain temperature at 0 degrees Celsius, pressure at 1 atmosphere, whatever ice is there melts into water, whatever water is there melts into solid like ice, freezes into ice, and this is the equilibrium that's established. One thing, because we just started this chapter, I need you guys to observe carefully is the symbol that I've used here. So when you have arrow facing forwards and backwards, so this represents that equilibrium हो रहा है, मतलब जितना हो रहा है forward process उतना ही backward process भी हो रहा है. So this represents a reversible process whenever we write it for chemical reactions equations, and in general this, because reverse bhi hai forward bhi hai, it's a reversible thing, and it also denotes equilibrium being established between whatever is there on both sides. Iska opposite, if I draw a proper arrow like this, it means that acha, it's going from left to right only. This is what you guys have seen till now in like chemical reactions and all, but once this comes into the picture, it's used to represent like something that is reversible. Both sides are taking place. Okay.
So ma'am, all equilibrium are like reversible, right?
Yeah. Otherwise, equilibrium established kaise hoga? Equilibrium by definition is forward equals backward. So.
Ma'am, I actually got disconnected after you were explaining the fifth point. What did you exactly do after that?
This only, we're starting with examples. So this is like this, if you keep temperature at 0 degrees Celsius and 1 atmosphere, there is an equilibrium established between ice and water. So whatever ice is there gets converted to water, whatever water is there gets converted to ice. Similarly, again,
Ma'am, also one more thing. Could you like go back? I just want to make sure I did not miss out anything.
okay, just 5 points.
All right.
Okay, the next process, H2O liquid, H2O gas. So this process is different from the previous one in that this can happen at any temperature, because liquid to gas conversion can happen during evaporation. It doesn't have to be boiling. And iska reverse process is condensation. Again, like you have something called a dew point, which when it is reached, like condensation can happen at any temperature. Okay, so this is a liquid vapor equilibrium. So in this case, the constant parameter, like in this case, vapor pressure is what is constant at a given temperature. Vapor pressure, although it's like something new and weird, like you haven't really worked on vapor pressure, you might have heard of the name. This is essentially like in the real world, this is what you feel as humidity. So vapor pressure के basis पे you can figure out, okay, what is the humidity present in the atmosphere or in the air or in the space above water. Okay. So this is always established. Like if you have liquid water anywhere, vapor pressure will always be there, and it is at a given temperature and pressure. That is why you feel the change in humidity between summer and winter more drastically, because the overall atmospheric, like the temperature of your surroundings is changing. So temperature affects this particular equilibrium.
Could you explain vapor pressure again?
Vapor pressure, okay, so vapor pressure haven't really gone like really deep into it. So basically, yeah, what happens is, if you have a water, like if you put water in a container, like let's take a closed vessel to keep this understandable, simpler. If I take a closed vessel and let's say I remove all humidity from the vessel by using like calcium oxide or just chemical processing, I remove all the humidity. Then so basically the air inside it does not have any water. Then I pour some liquid water into this container, introduce some liquid water in this container, and I close it. I close it because I don't want any interference from the surrounding atmosphere. Atmosphere mein hamesha water vapor rehta hai. I don't want that to interfere with it. Then if I put a barometer here and measure the pressure, it is observed that the pressure increases. Now, why is the pressure increasing? I'm not heating the vessel. एक room में it's there on a table, it's there on a counter, and it is closed. Matlab, there is no change as such that I am doing to it. It's just the water with like it's just a container with half filled with water. So what's going on? Why is the pressure increasing? The reason is
evaporating.
Correct. So there is evaporation of water going on, which means these water molecules are in like even though I removed all humidity from the air inside the container, I end up getting more water molecules here because this has started evaporating. Okay. Now, more number of molecules, right? PV equal to nRT. Closed vessel hai, volume is not changing. Temperature also not changing. I'm not heating it. I'm not cooling it. Pressure is also not changing because everything is at atmospheric pressure. So when N increases, so basically when N increases and V and T are all the same, the inside ka pressure also increases. So that is causing the particular change in pressure in the barometer. So this particular kind of pressure that is exerted due to the vapors of a liquid, because a liquid has evaporated then and there, and that particular vapor, that particular gaseous state is exerting pressure. So that pressure is called vapor pressure.
Ma'am,
Hmm?
what were the conditions inside the container? There was air, and then you put liquid water. Then
And then I closed it. I just let it be. I didn't do anything. I just put some water there.
what happened?
Then the pressure increased on its own. Why did the pressure increase? Because the water that is there starts evaporating.
But how would that increase the number of moles?
See, initially there was only like nitrogen, oxygen, carbon dioxide, atmosphere mein jo gases hai, only those molecules were there over here. But when water started getting evaporated, so ye particular gas mein, like in this particular space where the gas is there, usme water molecules bhi aa rahe. So that's basically whatever initial atmosphere mein jo molecules hai, plus the molecules of the water that has evaporated. So number of moles of the gas increased. So that exerts more pressure.
And how is this relevant to the example that you just gave? Like the H2O becomes H2O.
Coming to that. No, you asked what is vapor pressure, so I explained that.
Yeah, got
So at one point, so as the water molecules starts vaporizing, matlab forward reaction ho raha hai, liquid water turning into gaseous water. Once it has reached again the saturated point, like the maximum point ki itna water molecules hi evaporate ho sakta hai, then the reverse process gets kicked into this. So vapor pressure slowly increases until it reaches a point and then it remains constant. So whatever, like if you put a closed container, like if I put water in a bottle, all of it is not getting converted into vapor, right? In fact, you can't even figure out how much is converted into vapor because your liquid water tumne liya, that remains that much only. It's not changing. So the reason is that once this forward process reaches a point, the backward process starts kicking in. So whatever water is getting evaporated, yahan pe space se condensation kicks in and it goes back into liquid state. As long as you keep the temperature constant and the pressure obviously is like externally, you're not changing anything.
Ma'am, I didn't understand.
What part of it did you not understand, Kavya?
It go like when evaporation happens, uske baad condensation happens. How I didn't get that.
Evaporation kicks in, reaches a point of saturation. Now gas molecules are all roaming, right? Like they all are going here and there. At some point, two molecules will collide against each other. They will, like, again, because this is not an ideal gas, water is polar in nature, they will get attracted. So gas molecules going in all directions, some of it will be directed towards this. Yahan pe you have like adhesive forces, cohesive forces. They're going to attract the water molecule back in. It's going to become a liquid again.
So uska and vapor pressure का क्या relation है?
Kiska relation?
this process of evaporation and then condensation and vapor pressure, what is the relation? I can get that.
Vapor pressure is literally the pressure exerted by the vapor particles above liquid surface. So if you don't have enough vapor particles, then obviously your vapor pressure is going to change.
So like unless we have significant vapor pressure, this process will not happen. Then after evaporation, condensation, that.
I don't get it. Evaporation will always take place. Like you need to have correct
You need-
temperature and pressure. Like yeah, like if it's a very low pressure thing, or if it's like a very high temperature thing that the particles are just like zooming past each other, then there's not enough thing to hold them together, right? So condensation will kick in only after a certain point when the air is saturated with enough of that vapor. And this is not just for water, huh? Like I took water ka example here, but this is true for every single liquid. The extent, like kitna vapor pressure, like kitne particles vaporize honge, that will change. But the fact that there is a vapor pressure associated with all liquids, that is going to apply to all of the liquids. That fact is correct there, correct.
And this is not the same thing as happens in solid liquid equilibrium, right? That's different.
No, because it's solid and liquid, no? There's no pressure associated with solid, like only gases exert pressure. Okay.
So could you like give a small like what is exactly again? Could you like explain it in simple words?
How much simpler do you like? Can you tell me what you did not get? Then I can focus on that.
So is it just that it becomes vapor and when it collides it becomes liquid again? Is that what it is all about?
That's it. Becomes vapor, forward process, becomes liquid, reverse process. When it is in vapor form, it exerts a certain amount of vapor pressure. Yeah, that's
So
what that's
after the particles collide, the cohesive forces, or that whatever you said, that they are attracted and then they become water again.
yeah, that's just a driving force for condensation. That's just for your understanding because you asked the question. But the fact is that evaporation takes place. Evaporation ka exact reverse is condensation. So when evaporation takes place, the vapor pressure keeps increasing, and then once like it has reached saturation, like maximum humidity aa gaya, like for that particular temperature and pressure, then condensation starts kicking in until both of them are in equilibrium. Yeah, so this is the kind of equilibrium established between liquid and gaseous state. So that's evaporation is one process, condensation is the opposite process. So during this equilibrium, vapor pressure is the thing that you're going to track. So this is the constant. So we talked about every equilibrium characterized by one parameter, right? So in a liquid vapor equilibrium, that parameter is the vapor pressure. ठीक है? Clear?
Yes.
Rishad?
Yes, ma'am, got it. What I said was only like the simplest thing, right? That is correct only, no, what I said.
Evaporation happens, condensation happens. That's it. Next. So again, we touched on solid, liquid, liquid, gas, then solid gas also there's equilibrium. Sublimation, let's take iodine. So iodine solid. Sublimation में क्या होता है? What is
Solid to gas.
gas? So I2 gas. So solid to gas is sublimation. uska opposite is deposition. So even when you observe sublimation takes place, you can see that again, like because vapor is being established also depends on vapor pressure. That would be the constant this thing. Not just iodine, but even camphor. You guys know what camphor is?
The ball, the mod ball.
Huh,
It
like
reminds you if you fainted, right?
what?
It's
It's
used
that
for like
Kapoor wala thing.
revival.
It's used for viral. Oh, right, in Vicks, this thing, yes. Kaveri said mothball. It looks exactly like mothball, but the chemical composition is very, very different. So camphor,
It's used in like puja and all, right?
correct. How
Like
many of you
Kapoor,
are
I think it's called.
religious? Yes, absolutely.
I'm not, but my family is.
Yeah, my
So that's what I
family.
meant. Like, how many of you have seen like aarti and religious processes and all that? Yeah. So the white thing that you burn when you do aarti, that is camphor. So this is what you use in like, so Vicks ka inhaler hota hai na? So the thing that they put inside that inhaler is camphor. So that also sublimates, like that's why you get that smell and everything. Mothballs, yes. Ammonium chloride is another one. But yeah, sublimation, just like with liquid evaporation condensation, is maybe there's an equilibrium, that is. Any physical process that you take, as long as there is a forward and reverse, there is always going to be this thing. Dissolution ka, I have already discussed with you, solid liquid thing. Sanat, do you
Can
have
you
a
go
question?
back?
Yeah, Sanat, do you have a question or is that from before?
Oh, no, it's from before, sorry.
Okay.
Is deposition like the particles left out after the
No, no,
it's
no.
sublimated or something like that?
Ye reverse process, like gas turning into solid is deposition. Deposit word ho raha hai, like you coming across the word deposit, right? Like deposit ka matlab kya hai? Like putting something on it. So gas crystallizing into solid, that's deposition.
Okay, got it.
Then you have equilibrium involving dissolution of solids and gases. Solid ka मैंने already sugar
Go
water.
back for a second.
What's up?
Can you go back for a second?
Oh, yeah. Let me know when you guys have all done like noting it down. Iska hi, if you want, you can note down an extra example. Ammonium chloride also sublimates solid, sublimates into NH4Cl gas. Smira, Arnav, Adit, I think have mentioned. If anybody else also had like Keritu also did. Kaveri, Sanat, Rishabh, once you guys are done.
Oh, I'm done. I didn't
Okay.
do the reaction. Okay, yeah, I'm done. I'm done.
Kaveri?
Yeah, done.
Cool. Dissolution of solids and liquids. Liquids, sorry, solids and gases and liquids. Dissolving solids and gases and liquids. So about vapor pressure, right? we are going to deal a lot more about vapor pressure in grade 12. So we'll get deep into all these specific processes. So even dissolution, like the first chapter is called solution. So it's all about solids and gases being dissolved in water and the laws and everything related to that. Okay. Solid, anything solid, like this is something that I discussed. This is the example that I'd taken when I was explaining that thing to you guys. Sugar, solid, in equilibrium with sugar, aqueous. Aqueous means dissolved state. So the way they detected this is first they created a saturated solution of sugar in water, and then the extra sugar that they put in radioactive sugar. So radioactive sugar, matlab sugar is basically C12H22O11, right? So the carbon atoms used could have been C14, or instead of hydrogen, they made it with deuterium. So that way they could track, okay, we put in solid radioactive sugar, but they could detect that radioactivity coming from the solution. तो उससे पता चला कि oh, even though it is already saturated, some of it is going into the solution. The other one, like gases and liquids के लिए, one example is something that you all have seen in your daily life. CO2 gas dissolve in water. So CO2 aqueous. Where have you guys come across this? Do you know? Are you aware of this?
Aerated drinks.
Aerated drinks, yes, sodas. Coke, Pepsi, Fanta, 7-Up, all that. Okay. So again, we won't go deep into it, but I'll mention, I think this is there in your textbook. That's why I'm mentioning it. So related to the extent of how much, the forward process, reverse process. So iska related, there is something called Henry's law. So Henry's laws, like very simply put, basically, yeah, Kaveri.
I have a kind of a silly doubt. When everything is in solid, so in that way it should for that particular material, the presence should be possible in both liquids and gas as well, right? So if we're saying like sugar is in solid, why do we have to say it in aqueous? Can't we just write liquid?
No. So the difference between sugar aqueous, sugar liquid means, sugar liquid means that the sugar is literally in liquid state. Matlab you're melting sugar and getting, it in liquid form. Aqueous means sugar mixed in water. So say you will understand that sugar is dissolved in water. Sugar solid means it's just solid, like solid sugar, whatever is there in your sugar box. It's like that.
So it is aqueous is only written when a solid is then dissolved into a liquid, right? If it is already a liquid, then we just write it liquid.
Yeah, liquid means it's in molten form. That is literally liquid, like the way water is, the way oil is. Aqueous is then it's not solid or liquid anymore. Even if you take a liquid, like suppose you're dissolving HCl, or not HCl, what is a liquid in everyday life? Alcohol, let's say. If I take C2H5OH, if I say liquid, this is pure 100% ethanol. It's just ethanol in liquid state. But if I take C2H5OH in aqueous state, this means that it is ethanol mixed in water. So ethanol dissolved in water. And if I take C2H5OH solid, it means that, oh, I've taken this and frozen it. Like, think of it as ice cubes, but like alcohol cubes or something like that. Okay, clear? Difference between solid, liquid, aqueous. Yeah.
Yes.
Kaveri? Oh, I'm not able to hear you, Kaveri. So I can see that you're under mute, so I can't hear you.
Oh, we
think
don't have hand raised. I forgot to lower it. Sorry. I'm sorry.
But clear about this difference between molten, aqueous, liquid, solid. Clear. Right. Coming back to dissolving gases in liquids. Again, the word aqueous matlab, I have taken that CO2 gas and put it in water. It is dissolved in water. So aqueous specifically means water because aqua, aqueous, that Spanish, Greek, Latin, whatever. If it is dissolved in something else, then denoting this will change. Like you guys have come across ammoniacal, no? So if I write AM in brackets, it means that it is dissolved in ammonia. Anyway. Yeah, Henry's law. So this law is applicable whenever you're dissolving gases in liquids. So what it states is the mass of the gas dissolved is directly proportional to the pressure of the gas above the solvent. Okay. So basically, I mean, this makes sense, right? Suppose I'm trying to carbonate the water that is there here. Have you guys ever seen the process of carbonation? Like this at-home products like this Soda Stream, and even otherwise, like, have you guys ever seen?
Yeah, like where they carbonate water and all, right? They just like blast CO2 into the, like, whatever it is, I think.
There is some
kind of.
fish thingy, right? There is some fish thingy after you do it.
in drinks you have it.
Fizz is the CO2. Yeah. How many of
That's
you?
how soda and all is made, right?
Correct. Yes. How many of you have like seen this in videos or in real life? Like, how many of you are aware of this, and how many of you don't have an idea about it?
Could you repeat, ma'am?
Like the process of carbonation. How are sodas made, basically? Have you seen it in video, like using Soda Stream or that soda presser?
I feel like the Soda Stream ads, but I'm not like.
You've seen Soda Stream ads, okay? So usme they must show you, right? Like how that thing, that gadget is used.
I wasn't paying that much attention.
Never mind. Okay, 4 of you, like the guys have all seen it. Kaveri, Smera, Ritu. Okay, I'll just show a quick thing. How to use your Soda Stream. Soda Stream is essentially a company that created a gadget where you can create soda, like fizzy drinks at home itself. So you take water, or you take like sugar water, juice, whatever it is, and you do this process and it becomes a fizzy drink.
Thank you for choosing the SodaStream Source Home Soda Maker. In this video, we'll show you how to make your own sparkling drinks at home just the way you like them. Place the soda maker on a sturdy surface. Unscrew the cap. Remove the back cover, pulling it from the
Okay, we missed
carbonator maker on a sturdy surface. Remove the seal from the carbonator.
So they said carbonator. The reason why this is called carbonator is because it's a tank of carbon dioxide gas, which is like used, like it is compressed, it is stored under an extremely high pressure. So this is the source of the fizz.
And then unscrew the cap. Remove the back cover, pulling it from the hole. Insert the carbonator into the soda maker and screw it tightly into the holder. Do not use any tools. Then, replace the back cover and push it into place. You are now ready to start making your favorite sparkling drinks at home. Results are achieved when the water is cold. To insert the carbonating bottle, make sure that the carbonating block is in its fully upward position.
Oh, this is an important
at
thing.
home.
Okay.
Fill the carbonating bottle with water up to the fill line. Best results are achieved when the water is cold.
So she just said it. Best results are achieved when the water is cold. So temperature is really, really important. Higher temperatures, gases are not soluble. Lower temperatures, they are more soluble in water, which is why all your fizzy drinks are better when they're ice cold. So even carbonation, like dissolving carbon dioxide into this water, is better when it's cold. When it's warm, you need, like, it won't get dissolved. You need to work really hard, like, and it's not gonna taste good. So
Shouldn't it be the exact opposite? Because when it's warm, like the water would be closer to like there would be more space because the molecules would move farther apart, right? Because of their kinetic energy being increased. So it
That's a
should get
very
better
good
dissolved, right?
That's a very good point, Ritu. But look at what you're trying to dissolve. You're trying to dissolve a gas. So when you're trying to do it at a higher temperature, it means that the gas is also at the higher temperature. So the gas molecules also get equal power to move away. That is the reason, like, again, this point comes up when we do solutions in grade 12. In the case when you're dissolving a solid, then hot is preferred. But if you're trying to dissolve a gas, then cold is preferred.
I don't understand your.
Insert the carbonating bottle.
Doesn't matter. Like this, if for this, like we'll revisit it in grade 12. So don't worry about it now.
Make sure that the carbonating block is in its fully upward position and the bottle rest is angled forward. Push the bottle up and back. The snap lock will catch the bottle and in the bottom of the carbonating bottle and base. Please check the bottle is firmly in place before carbonating. LED indicator is illuminated, releasing the block halfway level of carbonation as indicated by the illumination of an addition.
The rest of it is the same. Like you put the tank, like the CO2 cylinder at the back in the beginning, and you put your water, and then when you press it, it basically, it like, because CO2 is at an extremely high pressure, that basically pushes the CO2 out into the liquid, and that's how CO2 is dissolved into the water or whatever liquid you're trying to carbonate. Okay. But yeah, so that's how you create sodas. And
Who buys this stuff? Who even buys this stuff?
oh, lots of people, you'd be surprised, Kaveri. It's not very popular here, maybe, but whoever
Like
likes
people who are training to be bartenders and all.
What if like the machine starts leaking and you get like carbon poisoning or something?
Oh, with carbon
If there's too
dioxide.
much carbon dioxide.
If there is faulty with the machine, you need to be more worried about an explosion than more than poisoning, because
Because it's like pressurized, right?
correct, all of this is stored under extremely high pressure. And the reason why it's like you work with such high pressures is because of Henry's law. As the pressure of the gas increases, the mass of the gas dissolved also increases. So if you want that maximum fizz, your carbon dioxide should be at that maximum pressure. Yeah. So that's the thing. And
If you give more carbon dioxide, will the fizz be for more time, or will there be more fizziness or something like that?
there will be more fizziness. How long that fizz is there for, again, that depends on the temperature, like the external temperature, and it also depends on the external pressure. Well, external pressure you can't do much with about, because it's just atmospheric pressure, but you can control the temperature. That is why you always store your cold drinks like sodas, Pepsi, Coke, Sprite, all of this in the fridge. Have you ever like left it outside?
Yes, several times.
So what happened when you left it outside?
Nothing. I just put it back in the fridge and hope no one noticed.
No, but like in terms of taste or the
The
feel.
fizz goes away.
Yeah. The reason why the fizz goes away is because, you know, when you put it in the fridge, it's at cold. Like fridge ka temperature is as low as 4 degrees Celsius. That's what is recommended for fruits, veggies, and all that. So from 4 degrees Celsius to, you're slowly increasing it to what? Room temperature would be around 25 plus or minus. So as the temperature increases, the solubility of gas decreases. So the carbon dioxide, you know, as it gets warmer and warmer, it gets more kinetic energy and escapes from the drink out into the atmosphere. And once it's in the atmosphere, you can't put it back in the drink. So you lose the fizz. Yeah. So that's the thing.
So once we lose it, then the taste also goes away.
Yeah. Like once you lose the fizz, at least Sprite is literally just sugar water. Like read the, what do you call it? Ingredients list. Gives you an idea.
But ma'am, as advertised, we can use a soda stream carbonator to make it sweet again.
Yes. So Henry's law mathematically, so mass of the gas dissolved, if it's directly proportional to pressure, you introduce a proportionality constant, KHP, where KH is called Henry's constant.
What does above solvent mean?
Above solvent. So basically, if this is the container where you're planning to dissolve a gas, then whatever, like if you're trying to dissolve it, you're putting gas through here. So yahan pe jo bhi pressure hai, it depends on that. So that's why in the soda stream, you're completely sealing it up. So the bottle is in such a way that it's completely sealed till here, and the gas above the solvent, like if you fill the water, juice, drink, whatever till here, you put that tube pipe over here, and so this particular portion of it should have like high pressure, so that leads directly into that high pressure CO2 tank. So essentially, like for your understanding, think of it as the pressure at which you're dissolving the gas. Yeah. So there's applications related to it. Just a moment. Yeah, so there's applications related to it. You can study it, deep sea drivers and all that. Yeah, so these are like some examples of physical equilibria. Then we have equilibria in chemical processes. How are you guys feeling?
About the chapter, like physically.
Right now, yeah, like too much info.
It's going pretty good.
Okay. No, do you want to take like a 5-minute break or should we continue?
No, I'm interested.
Can we take a quick 5-minute break so I can get some food?
Yeah.
Ma'am, I got disconnected. Could you please show the previous slide once?
Yeah. I'll keep this on. We'll resume at 5 o'clock. It's 4:56. We'll take 5. Okay. All right. Who all are here?
Hi.
Okay, Adit, Arnav.
Could you go back?
What are you doing till now? I just,
Wrong emoji. I'm sorry.
that's okay. Anything for me to know that you're here. It's fine. Smera is
No,
good.
I have a doubt. I don't. I'm not. So basically, I want to know, like, uh, so in dissociation of solids and gas, it's basically just, gas to liquid and liquid to gas. Is it just like that, or maybe
Wait, what?
solid to liquid, liquid to gas?
Where?
The
Which pro-
like the part dissolution of solids and gases and liquids,
Hmm.
that basically means like the reversible process of solids and liquid, or between liquid to gas, right? It's between those, right?
No. Read properly. Dissolution hai ye. I'm talking about dissolution, matlab the process of dissolving. So dissolving of solids and gases in liquids. So I'm taking a liquid like water and I'm dissolving a solid in it. So the equilibrium established between the solid and its dissolved form in the liquid. Similarly, gases ka bhi I'm taking the same thing. So I'm taking a gas and then I'm trying to dissolve it in a liquid. So the equilibrium established in this process. Okay, so read through the whole
Okay, got it now.
stuck on like acha solids, gases, liquids, nahi, like don't be fuzzy about things. Like read the whole thing and understand. Okay. All right. Kaveri, Sanat, you guys here?
Yes, ma'am.
Kaveri is here.
Yes, ma'am.
Okay, excellent. So we'll start about chemical processes. Funda is the same thing. Forward, same as backward, but this time we're looking at chemical process, matlab chemical reactions. Okay. So again, since we are considering a reaction happening and uska reverse process also happening, so chemical equilibria are applicable to something called reversible reactions. Okay, so reversible reactions. So you guys have heard of it. What do you mean by reversible reactions?
Like reactions where you can obtain the reactants back from the product.
Correct. Okay. So in the case of a reversible reaction, like let's say we have a reversible reaction, when do we get an equilibrium is when the rate of forward reaction is equal to the rate of the backward reaction. Okay. So in this situation, when the forward reaction is equal to the backward reaction, then one thing that we notice, like the parameter that does not change, happens to be the concentration of reactants and products. So this does not change. It does not change with time. So even if, like 10 minutes ho raha hai, 15 minutes ho raha hai, but the concentration of reactants, products, like everything remains the same. So at this point, we say that there's a chemical equilibrium. Okay. So let's take like an example. Okay. So let's say I have a reaction A plus B. Reversible hona chahiye. So I use the symbol, gives C plus D. Okay. Now we're looking at like concentration of reactants products, not change, time. So time is like a major, like that's a factor we're looking at. So let's measure those particular quantities like with time.
Ma'am,
Hmm?
I didn't get what that meant, like concentration of reactants and products doesn't change with time.
Yeah, that's what I'm going into. Like this time I took an example, so I'll go deeper in that. So reaction hai. So for this reaction to happen, what do you take in a vessel? Ye
A
reaction,
and B.
you take A and B. So A and B are the reactants. Okay. So at time t equal to 0, bas just abhi liya reactants vessel mein. If I measure the concentration of reactant at time equal to 0, kya hoga?
Could you repeat?
So what will be the concentration of the reactants at time equal to 0? Ekdam beginning mein.
A plus B.
A plus B are the things, right? Like they are the reactants. Like imagine A and B to be carboxylic acid and ethanol. Unka concentration kya hoga? Like will they be 0 or
1.
matlab maximum value, like whatever concentration you have taken, right? So it's going to be somewhere over here. As time goes by, like abhi like A plus B liya, you mix them. What will happen to the concentration of the reactants? Is it gonna remain the same? Is it gonna increase? Is it gonna decrease? Like kya hoga?
It will decrease.
Decrease, क्योंकि ये react होके they are changing into C and D. So eventually it's gonna decrease. It's gonna look something like this, okay? It's not a straight line, like the decrease is, there's a curve to it. Now let's look at C and D products. Use a different color, better. At time t equal to 0, what will be the concentration of C and D in this vessel?
Could you
0.
repeat, ma'am?
Rishit said 0. Ritu, what did you say?
Could you repeat? Like your voice was breaking for me a little bit.
Oh, at time t equal to 0, at the very beginning, what will be the concentration of the products?
0.
0, because they don't exist yet. Abhi tak humne A, B hi kiya. Okay, you start at 0. Then as time goes by, 1 second, 2 seconds, 3 seconds, what will iska graph look like? Concentration of products.
The
Same
reverse
like
of
the
reactant.
reactants, but you reverse.
Opposite way. Rather, it will be increasing and then it will be like stable.
Correct. Increasing is what I was looking for. Kind of looks like this. Yeah. So as time goes by, like as the reactants decrease, at the same time, the products increase because the reactants are literally changing into products. Okay. Now,
Ma'am, could you this again?
repeat. So Kaveri, you like, that's why I ask questions. Stop me then and there itself if there's something that you don't understand. So from what point, like what exactly have you not understood? Like what exactly do you want me to repeat?
Like the part that you highlighted.
Highlight, like you got the graph, like the blue and the maroon lines, concentration of reactant decreasing, concentration of the product.
Yeah, that I understood.
So like why does this decrease, this increases? Your reactants are literally changing into the products, right? So yeah, as the reactants decrease, your products are going to increase. So like if one molecule of A and B have gone, that means that one molecule of C and D have been produced. If two of these have gone, it means that two of these have been produced. It's kind of like that, right?
Yeah.
So that's what. So as this decreases, this increases. Both happen simultaneously. Now, I want you guys to imagine what is happening in this beaker, the reaction itself. So you have a lot of A and you have a lot of B. Now, reaction happens when a molecule of A and B are colliding with each other. That's when, the reaction happens. Like, that's when the reaction is capable of happening. That's where the bonds break, new bonds creating, all of that happens. Like, clear, like accepted?
Yeah.
Yeah.
Yes, ma'am.
Collision needs to happen for the reaction to take place. Yeah. So, थोड़े बहुत collisions हुए. So, in the mixture, eventually, AB हटा के, I got a bunch of C's and D's. Now, slowly, as the amount of product is increasing, matlab reaction vessel mein, along with AB, I also have like a whole lot of C and D molecules also. So when I have enough CD molecules that a molecule of C collides with a molecule of D, like all of them are in the same beaker, right? All of them are in the same container. So it's not necessary that they all stay in their own lane. C and D are bound to collide with each other at some point. So when that happens, the reverse reaction kicks into gear. Okay. So whenever A and B collide with each other, CD is formed. Whenever CD collides with each other, A and B are formed. So there will come a point where the rate at which C and D are being produced, the forward reaction takes place, is equal to the rate at which A and B are also being produced. Okay, so rate of the forward reaction is equal to the rate of the backward reaction. Now, because I have CD also being produced and simultaneously AD also being produced, all of them at the same time. So after time t, my graph is going to be two parallel lines. Matlab, the concentration of the reactants denoted by the blue line. Yeah. So concentration of reactants A and B and the concentration of the products C and D does not change. They're parallel lines. So time is changing, but the concentration remains the same. They're at this point only.
After the reaction happens, the products and reactants both still stay in the container.
Yeah. As the reaction,
Oh.
you're not gonna jump out of the container, right? Like all of them are still there in this beaker only, unless you do something to change that.
No, but you would assume that they would be used up to make the reactants, right? All the product. All the reactants would be used to make the products, right?
But that's what I said. They are used up to make the product, but when like reversible reaction hai na, so when the product molecules collide with each other, ye backward reaction bhi chal raha hai. So then some amount of reactants are produced again.
Backward means what? Like,
so forward is A plus B gives C plus D. The backward is the reverse of it. So C plus D gives A plus B. So forward is how you read it normally. Is tarah ka reaction. So A plus B gives C plus D. So backward is literally the backward reaction. So follow this backward facing arrow. So that is C plus D gives A plus B.
okay, got it.
Okay.
So when you say that it does not change with time, only after like the dotted line that you've drawn, only after that it doesn't change with time.
Correct. So basically, after the dotted line, so when you observe that the concentrations are not changing, it means that there is an equilibrium established at that point. So that's what chemical equilibrium is. So Ritu, that's what I meant. So concentration of the reactants and the products, it does not change with time. So if you pick, let's say, reactants का concentration, तो forward reaction की वजह से the concentration of reactants are decreasing, sure, but because of the backward reaction, the reactants are also being produced. So whatever is decreasing is cancelled out by whatever is being produced. Similarly, if you look at it from the point of view of C or D, forward reaction की वजह से it's being produced, but because the backward reaction kicked in, they also get used up. So net thing is like whatever is being produced is being cancelled out by whatever is being used. So
Used for again making the reactants.
yeah, that's what the backward. तो यहाँ पे जो भी CD produce हो रहा है, they get used up because of this reaction to make A and B. So that's why reactant and product दोनों का concentration will not change. Now it's important to note that this happens after some time. That's why I drew a dotted line here. Now, how much time will it take? Like after how much time this thing is produced, like equilibrium is created, will depend on a lot of factors. It depends on the spontaneity, like how feasible the forward reaction, backward reaction is. It depends on the temperature. It depends on the pressure. So that's what we're going to study in this whole section, this whole chapter, the first section of it. So कुछ reactions के लिए this is like equilibrium बहुत पहले इधर ही form हो जाएगा. Some reactions will go to like 99% completion and then it is established. For some reactions, it may happen at like 50% completion. So that will change depending on all these different factors. But usually equilibrium matlab, this is what happens in the reaction vessel.
So, ma'am,
Yeah.
the like for reactions which equilibrium forms later, are they like less stable?
No. If equilibrium is forming much later, equilibrium is forming after like 99% completion, that is more preferable because it means that forward reaction chal raha hai, like you can use that reaction for something. But if equilibrium is formed after using just like 3% of the reactants, it means that the backward reaction is so powerful that as if like it got kicked into nature just like that. So it means that, you know, the forward reaction, it will be difficult to push through it. Then you need to change the pressure, you need to change the temperature, like do something about it.
Ma'am, if like A plus B, let's say, is more dominant than C plus D, would we still call that equilibrium?
No. I mean, like, what do you mean by more dominant?
Because then you had explained that initially that reaction would be faster than the other way around, right? So that would never attain equilibrium.
That will attain equilibrium. It will just kick in much later. Like let's say 99% of A and B have been used up to create C and D. So there's just like 1% remaining. Then that 1%, you know, of C and like A and B is constantly being created back. So equilibrium will be established. Just when will it be established during a reaction? Like right at the beginning or somewhere in the middle or towards completion? Like that depends on, yeah, A, B, C, D, and also like the temperature and the pressure and the heat and all of this.
Okay.
Yeah. Okay. So this is all to do with chemical equilibrium. Like reaction में equilibrium कब होता है, कैसे होता है, all of that.
Ma'am,
So-
just a second.
You're noting it down?
Yeah.
Okay. Let me know when you guys have noted it down. And also if you have understood it. If there's any part that you want me to explain again, we'll go over it. Otherwise, we'll move on to characteristics of chemical equilibria. A lot of it will overlap with what we did in physical equilibria. So yeah.
All the acids have like an equilibrium or just like the reversible ones?
Reversible ones. Because if it is irreversible, if reverse, like a backward process cannot happen in any way or form, so फिर C and D will not react to give A and B, right? So equilibrium कहाँ से आया? Only the forward thing is happening. So equilibrium matlab we're talking about reversible reactions. Okay. So somebody had reacted, no? Arnav had indicated khatam ho gaya. Okay. Smera is done. Okay. Shut down. Okay. So just like how we started off the chapter with characteristics of physical, this is characteristics of chemical equilibria. Again,
It's what we did for physical was that example 1, 2, 3, 4 thing.
yeah. 1, 2, 3, 4, what we started off with. Similar stuff, but what in like chemical context. A lot of it is overlap. Like equilibrium, matlab, it's going to be the same, like forward equal to reverse. So you have the same characteristic pretty much. Like the first point, at a given temperature, so at a given temperature, the pressure, concentration, density, color, all of that is going to be constant parameters, like basically the measurable properties that we saw in physical equilibria. Here also, density, concentration, these are the measurable properties. Color, all of that's going to be constant. So if you change the temperature, you're literally changing the reaction mechanics. So then the equilibrium will change and these properties will also change. So this is quite important. Whenever we talk about any sort of equilibrium, it is at a certain temperature. The temperature is constant in that case. Okay. You can attain equilibrium, like you can get it from either side. So this is a new thing, this we didn't see with physical equilibrium. So either side matlab, either you can start the reaction with A plus B and you get C plus D, and then at some point equilibrium will happen. Or you can take the product CD, let the reaction happen, like A plus B will be formed, and at some point equilibrium will happen. So agar koi reaction mein you see that equilibrium is happening, it means that it doesn't matter whether you start from the forward side or the backward side. You can get it from either side. You can take either this as the reactant or this as the reactant. Doesn't matter, you'll still get equilibrium.
Why can't this happen in physical equilibrium?
You know what? Technically, yeah. Like you can get it with physical equilibrium also. Yeah. There's reversible process hai na? Absolutely. You change up the conditions. Like if you're doing it with evaporation condensation, instead of starting with a bowl of like a container of water, you can start with, like you take an empty container and then a highly humid create a highly humid atmosphere, and then change the temperature so that condensation takes place first and then evaporation kicks in. You can start from either side. It's practically not very feasible for physical equilibrium. Yeah, because some processes are, because when you're trying to achieve something at room temperature, like that's what you're doing in case of dissolving or evaporation or freezing, you start with something at room temperature, right? Because to do the reverse process, then you need to change up the temperature pressure conditions, need to spend energy on that. So with chemical reactions, like all these chemicals are readily available, like either you can take this chemicals or this chemical, so it kind of makes it's more relevant in this situation. Next, again, this is very specific to chemical equilibrium, the effect of catalyst. So if you use a catalyst in the reaction, the equilibrium is not affected, just that equilibrium not affected, just that it is achieved faster. Okay. So what this means is, suppose I have the same reaction, A plus B gives C plus D. Suppose equilibrium is achieved at, let's say, 90% of the reactant. Like when you have 90% of the reactant remaining, that's when equilibrium kicked into motion and everything remained the same. Then if I use a catalyst, equilibrium will still take place at 90% of the reaction, just that agar without catalyst, if I got it after like 30 minutes, half an hour after reaction started, with catalyst, I'll get the same equilibrium in like, I don't know, 10 minutes. So the equilibrium is not affected. When do you get equilibrium? What are the concentration of the reactant product? All of that will remain the same. Just that only the time factor will change. Equilibrium is achieved faster. Like the reaction gets faster. That's it. Okay, in this case also the same thing. At equilibrium, things are dynamic but stable. Stable matlab they'll stay as it is for a long time. Wo reaction will keep happening forever if you don't change anything. Then yeah, extension of 0.4, it'll continue indefinitely if conditions are not changed. Okay. Then last point, same as physical equilibria, the magnitude of these quantities, like what is the pressure in the vessel or what is the concentration. So that indicates to what extent the reaction has occurred. Magnitude of the measurable properties. Indicates the extent to which the action occurred before equilibrium. Okay, so basically, again, reaction happened when there's 90% of the concentration of the reactants left. So if I'm like tracking the concentration of the reactant initially maximum like 100% था, उसके बाद goes down to like 50%, like 100 say 99%, 98%, 96%. That way it keeps reducing. So as you measure the concentration, it indicates कि okay कितना reaction हुआ है before the equilibrium, because once that equilibrium is achieved, that number will remain constant. So if like reactants, products, if they are gaseous, then you can track it using pressure. Color is another thing, you know, if reaction may change of color aa raha hai, then you can see, okay, like from lighter to darker or darker to lighter, you can track that change in color that way. Okay, so these are characteristics of chemical equilibrium.
Can you explain the 6 point again?
So it's exactly like what we discussed in physical equilibria. तो वहाँ पे क्या बोला हमने? So if you keep measuring these parameters, pressure, concentration, वहाँ पे vapor pressure, like all of that was there. But in the case of reactions, you mainly track the concentration or the pressure, depending on the type of reactants and products. So like imagine, let's say A plus B is reacting to give C plus D. So pehle 100% was reactants only. But as time goes by, t equal to 1 second, 2 seconds, 3 seconds, 4 seconds, and so on, the concentration of the reactant also will keep decreasing, right? So 100% reactant, abhi bas 99% will be reactant. Then 98% will be the reactant. Then 96% will be the reactant. Then 93% will be the reactant. So that way it'll keep changing. So if you keep measuring the concentration of the reactant, ki kitna hai concentration, it'll tell you how much of the reaction has happened. Eventually, till you get to the point of equilibrium, where let's say only 10% of it is reactive. उसके बाद 10% ही है. मतलब ओके यहाँ पे इक्विलिब्रियम एस्टैब्लिश हो गया.
So then can we say that concentration at equilibrium of like reactant and product is like 50-50?
No. So that's what I was explaining, Ritu. So that completely depends on what reaction it is. Like what are the reactants, what are the products, what temperature it's happening at, all of those factors. Equilibrium can be established at any point of time. It can be established immediately once the reaction starts at, you know, only 2% of the reactant gets used up. When it is at 98%, it can kick in. It could be at 50% also, can't say. It could be after 99% are used up. Matlab, 1% of the reactants are only pending. Kahi pe bhi ho sakta hai. That absolutely depends on which reaction it is. So this particular line, it can be established over here, it can be over here, it can be over here. That depends on many different factors. So that's an important point that you guys have to understand. It is not reactants equal to products. It is the rate of this process is equal to the rate of this process. So that's irrespective of, like, yeah, it depends on the concentration of reactants and products, but it doesn't mean that they are equal. Only the change that is occurring, that's equal. Clear? Rishit, Ritu?
A little bit, like it's confusing, but I get it.
Mm-hmm. Would it help if I took like hypothetical values?
it
No,
would.
like you keep saying that they're equal, like they're in equilibrium, but I don't get what is equal. Like there must be some value that's equal, like across the arrows.
Yeah, the process, like the rate at which this is being converted to this is equal to the rate at which this is being converted to this. I'll simulate an experiment. Okay, I'll help. So let's say A plus B and C plus D. I'll take random hypothetical values. Okay. So initially, let's say the constant, like stoichiometric coefficients also, like everything is 1:1:1:1. Let's keep it utterly simple. In fact, let's just take reactant changing into product. एक reactant हो सकता है, 2 reactants, 3 reactants, whatever. There are multiple reactants changing into products. Let's say at t equal to 0, 100% of it is reactant. Let's say I took 100 moles of the reactant. Product is 0 moles. Then reactant started changing into product. T equal to 5 seconds, then 10 seconds, then 15 seconds. So all of this is time. 20, 25, 30, 35 seconds. Okay. Let's say I started measuring every 5 seconds ki what is the concentration of the reactant, what is the concentration of the product. So if let's say 5 moles or 10 moles of the product got used up. If 10 moles of are reacted, how much would you expect there to be left in the vessel? If you calculated concentration of the reactant, what will be the concentration of the reactant?
100 minus X moles.
I'm saying 10 moles have been used up.
90 moles.
90 moles. Or how much of the product would I have?
10 moles.
10 moles. So the 10 that was used up in being changed to this. Okay. Or 5 seconds ke baad, let's say another 8 moles have been used up. So yahan pe when I measure the concentration, what will be concentration? Like how much of the reactant is there in the vessel?
82.
82.
Product kitna rahega?
18.
18.
So similarly, 15 seconds ke baad, I measure it. And let's say this has further reduced to 76 moles. This has reduced to, this would be increased to how much? 24 moles. Then this becomes 70 moles. This becomes
30 moles.
So then this becomes, let's say, 66 moles. This becomes 34 moles. Then slowly this keeps reducing, this keeps increasing. Then suddenly you'll hit on a point like product ka when I have sufficient, let's say not 35, maybe I keep measuring. Then let's say like 5 minutes later, I'll put a line. There's a time skip here. So 5 minutes later, I see that the reactant, there's as it reacted, there's only like 15 moles of the reactant that is remaining. And product, 85 moles of the product has formed. At this point, there is so much of the product that the backward reaction will kick in. So from these 15 moles, even if the amount of reactant has decreased, the amount of product will still remain, like, because this is also being converted to reactant. there's extra being formed. So 5 minutes ke baad, every time I measure, my concentration is stuck at 15 moles and 85 moles only. Yeah. The reason why this is there is, it's not that the reactants are not reacting, like the reactants are reacting. 15 से 12 होना था, but whatever 3 moles have decreased here, the products have also reacted to form the reactants back, so that 3 moles keeps getting cancelled at every step once it reaches the equilibrium. Okay. So you can see that concentration of the reactants is not equal to the concentration of the product, but it remains the same over time. Concentration of reactants is always at 15 moles, no matter what the time is. Concentration of product is always 85 moles only. But the rate at which it is converting, like यहाँ पे if there is -3, यहाँ पे +3 होना था. But reverse process में again 3 moles is getting converted to give 15 moles again. Yeah, Kaveri?
So basically, with time, the rate is like the not that the concentration is not changing, because both the reactant side and the product side, they are nullifying each other out.
Correct.
In the end, they remain constant.
Yes. So the concentrations remain constant. They are not equal, they remain constant. And the nullifying thing, so that's where the first statement comes into picture. The rate of the forward reaction, like by how much ever the reactants are decreasing, is equal to the rate of the backward reaction. So the equal amount is being formed again. So that's the nullifying thing that's happening.
I didn't get like the +3 -3 part.
So यहाँ पे I we went stepwise, right? 10 moles are used up, then 8 moles are used up, then 6 moles are being used up, then 4 moles are being used up. So that way, X moles keep getting used up of the reactant to produce that much amount of the product, right? So like once equilibrium kicks in, let's say iske baad 3 moles are used up. Which means that yahan pe it like this should like this is supposed to go like this is supposed to become 12 and this is supposed to become 88, right? But because it has reached equilibrium, because 85 is too much of the product, 88 mein se 3 moles gets used up to produce 3 moles of the reactant. So then 88 minus 3, this will turn back to 85 again, and ये 12 से फिर 15 बन जाएगा. So 3 moles of the reactant keeps getting used up to produce the product, but equal amount of the product is getting used up to give the reactant back. So that 3 and 3 keeps getting cancelled, and so your concentration will remain at the same point.
Understood, ma'am.
Right? Yeah. So that is equilibrium. Yeah. Yeah. So that's all about equilibrium. Then you have types of chemical equilibrium. This is very, very easy. So you have homogeneous equilibrium, and you have heterogeneous equilibrium. Again, come across homo and hetero. What do you expect? How does this classification happen? Guys, any guesses? Homogeneous matlab what remains the same and what is different in this?
Maybe for the first one, we cannot see where
state of the
equilibrium has
equilibrium.
been done.
No, Sanat, what did you say?
The state of the equilibrium.
Equilibrium
Like
का कोई
if
state नहीं है. It's not like
no,
equilibrium
like the
is not-
reaction, like if it's solid, then if the reactants are solid, then the
Ah,
product will also be solid.
there you go. Ritu, concentration, well, every equilibrium concentration of reactant products is constant. So Sanat has got it correctly. So this like homogeneous heterogeneous classification is based on the phase of reactant and product. So all reactants and products are in the same state or same phase. So all of them are solids or all of them are liquids or all of them are gases. Heterogeneous ke case mein reactants products can be like you can take two aqueous solutions in liquid state and then end up getting a gas out of the chemical reaction. So state badal gaya, that will be heterogeneous equilibrium. So we have a couple of examples also here. So H2 plus I2 gives HI, 2HI, balance it. So all of them are in the gaseous state. Hydrogen is a gas, iodine is a gas, and hydrogen iodide that's formed is also a gas. So this particular equilibrium, like this would be a homogeneous equilibrium. So different states, matlab, decomposition of calcium carbonate. So CaCO3, solid, when you heat it up, you get lime, CaO, which is a solid because it's a salt, and CO2 is produced, carbon dioxide is a gaseous. It's not gas, should be solid. So solid hai, theek hai, solid hai, but different phase. So this is a heterogeneous equilibrium.
Phase matlab state.
Phase or state, yeah. Change of phase, like phase change. So the reason why we use phase is thermodynamics mein you learned state matlab you have defined state functions like pressure is a state, temperature is a state, enthalpy is a state. So that is why we use the word phase to like clearly identify that, oh, solid, liquid, gas, like that. That's it. So you can look at the book. There are a few more examples given. You can like take a note of all of them. That's all. The
Ma'am, these
remaining,
are the types of chemical equilibrium, right?
yeah. So homogeneous is one type, heterogeneous is one type. The classification is purely based on like look at the reaction, look at what is the phase of the reactants and products. If all of them are the same, then it is homogeneous. Even if one of them is different, it becomes heterogeneous. इसके बाद we have the law of mass action. And equilibrium constant, Le Chatelier's principle. Okay, it's definitely gonna take like 4 classes, guys. We also spent like a whole hour on doubt clarification today. So yeah, from this point on, we're going to have like mathematics butting in. Yeah.
Ma'am,
Hmm?
so I have a doubt in the previous one only. This one I understood properly.
Hmm.
But for the previous one, I didn't get as Ritu asked earlier too, I was just thinking about it, but I still didn't get it. What about the +3 -3? What exactly is that concept? I still didn't get it.
See, if reactant, once it reaches a certain point, let's say in this case 15 moles, uske baad, as the reaction is going on, 3 moles of reactant will get used up. Like 3 moles will react to give 3 moles of the product. Okay. So technically, I wrote it in red here. ये 12 होना चाहिए, ये 88 होना चाहिए. But at the same time, 3 moles of the product is also reacting to give me 3 moles of the reactant back. So 12 से फिर वापस ये 15 हो गया और 88 से वापस 85 हो गया. So that's what keeps happening from this point on. How much ever reactant is used up to create the product, same quantity will be used up to create the reactant back again. So the rate at which reactant is used up is equal to the rate at which the product is formed. So from the outside, if I measure the concentration, because reaction, like all of them are happening at the same time, instantaneously it's happening, no? So I won't get to see ye +3 -3 ho raha hai. If I measure the concentration from this point on, because of this, I'll see that it is at 15 moles constantly. Like 5 seconds, 10 seconds, 15 seconds, doesn't matter. So as long as I keep that vessel unchanged, this will be the permanent concentration of the reactant. This will be the permanent concentration of the product. Ye change nahi ho raha hai. So that is the characteristic of the equilibrium. Ki the net concentration of the reactants and the products will not change. But what is an equilibrium is the forward reaction that R is reacting to give P is same as the backward reaction, P reacting to give R.
But there is for example, for this one, like you said, right, 85 moles is like it overpowers the reactant, so that is why it's also giving it back. So this one, the value which you are technically, if was the case, it was found out experimentally that this was there, or there is some rule that after it's just a bit of majority, then it will be equal or something like that.
No, experimentally, that's what has been observed. So people did some analysis ki kya ho sakta hai, kya ho raha hai. Like this is how it, like the whole point about equilibrium, kaise ho raha hai, kya ho raha hai, this is how it was established. This is what this graph represents. So I'm measuring the concentration of the reactants, which is like reducing as time goes by. But after a certain point, ये तो straight line बन गया. मतलब constant hai, whatever value this is. Same thing happened with the concentration of the products. Like theek hai, increase ho raha hai, makes sense, right? Reaction ban raha hai, matlab this will increase. But after a certain point, this becomes constant. Like this also became a straight line. It got stuck at, whatever this value was. So that's when, like then they looked at, okay, why is this happening? What is happening? Why is it not changing? They tweaked some things, like dissolution made it took radioactive sugar, right? Like that way they put some tracker molecules and did the reaction. They did it multiple times using different concentrations. So that's what this whole chapter is. Like we're studying ki equilibrium, kaise hoga, kya hoga, what is the significance, what can we do with it, all of that. Concentration change nahi ho raha hai. Excuse me. Sorry, yeah. So concentration is not changing. Why is it not changing? Like reactant hai, matlab reaction hona chahiye na? That's the whole thing about reactions. So why is it not changing? Because the backward reaction is also happening at the same rate. Yeah.
Got it.
Hmm. Okay, so rest of the things, it's almost 6 o'clock. Law of mass action and the equilibrium constant and all will start next class. So I have put a class tentatively for Saturday. You guys free on that day?